Now, what does the perceptron learning algorithm do? Okay. Now, what it does is this complicated figure, which takes the evolution of E in and E out as a function of iteration. When you apply the perceptron learning algorithm, you apply it only to E in. E in is the only value you have. E out is sitting out there. We don't know what it is. We just hope that E in tracks it well. Okay? So let's look at the figure. These are the iteration numbers. So this is the first misclassified example. You go and apply the perceptron learning algorithm again for 1,000 times. As you do that, E in, which is the green curve, will go down and sometimes will go up. We realize that the perceptron learning algorithm takes care of one point at a time and therefore may mess up other points while it's taking care of a point. So in general, it can go in up or down. But the bad news here is that the data is not linearly separable. And we made the remark that perceptron learning algorithm behaves very badly when the data is not linearly separable. It can go from something pretty good to something pretty bad in just one iteration. Okay? So this is a very typical behavior of the perceptron learning algorithm. So because the data is not linearly separable, the perceptron learning algorithm will never converge. So what do? We force it to terminate at iteration 1,000. That is, we stop at 1,000 and take whatever weight vector we have, and we call this the G, the final hypothesis of the perceptron learning algorithm. Okay? Now, you obviously look at this and you say, okay, if I only took this guy, this is a better guy than the other guy. But you are just applying the algorithm and cutting it off. Okay. Now, one of the things you observe from here, I plotted E out. You are not going to be able to plot E out in a real problem that you deal with if E out is really an unknown function, okay? You may be able to estimate it using some test examples and whatnot, but all you need to know here is that E out is drawn here for illustration, just to tell you what is happening in reality as you work on the in-sample error. And in this case, you find that E out actually tracks the E in pretty well. Okay, there is a difference. So if we go from here to here, that's our epsilon. Okay, it's a big epsilon. But the good news is that it tracks it. When this goes down, this goes down. When this goes up, this goes up. So if you make your decision based on E in, the decision based on E out will also be good. That's good for generalization. And that is one of the advantages of something as simple as the perceptron learning algorithm. It doesn't have too many parameters. And because of our efforts in getting only 3 features, it has even 3 parameters now. So the chances are it will generalize well, which it does. Okay. Now, what does the final boundary look like? Okay. So this is only the illustration here is just, okay, this is the evolution. Eventually, you end up with a hypothesis. The hypothesis would separate the points in the scatter diagram you saw. So what does it look like? Well, it looks like this. Okay, so this is your boundary. This is the final hypothesis that corresponds to the hypothesis you got at the final iteration. Well, it's okay, but definitely not good. It's too deep into the blue region. You would have been better off doing this. And the chances are maybe earlier guys that had better in-sample error will do that. But that's what you have to live with if you apply the perceptron learning algorithm. So now we go and try to modify the perceptron learning algorithm in a very simple way. That is the simplest modification you can ever imagine, okay? So let's see what happens. This is what the PLA did, right? And when we looked at it, we said, okay, if we only could keep this value. Well, this value is not a mystery. It happened in your algorithm. You can measure it explicitly. It's an in-sample error. And you know that it's better than the value you ended up with. So in spite of the fact that you are doing these iterations according to the prescribed perceptron learning algorithm rule, modify the weights according to one misclassified point, you can keep track of the total in-sample error of the intermediate hypothesis you got, right? And only keep the guy that happens to be the best throughout. So you're going to continue as if it's really the perceptron learning algorithm, but when you are at the end, you keep this guy and report it as the final hypothesis. What an ingenious idea, okay? Now, the reason the algorithm is called the pocket algorithm, because the whole idea is to put the best solution so far in your pocket, okay? And when you get a better one, you take the better one, put it in your pocket, and throw the old one. And when you are done, report the guy in your pocket, okay? We can do that. So what does this diagram look when you are looking at the pocket algorithm? Much better. You can look at these values, and it is the best value so far. So here we went down, and here we indeed went down. Here we went up. You see this green thing, okay? Here we didn't, because the good guy is in our pocket, and that's what we're reporting the value for, okay? And we continued with it until we dropped again, and we dropped again, and we never changed that, because there was never a better guy than this guy. So when we come to iteration 1000, we have this fellow, okay? Now, when you do that, you can use perceptron learning algorithm with non-separable data, terminated by force at some iteration, and report the pocket value, and that would be your pocket algorithm, okay? And if you look at the classification boundary, PLA versus pocket, this is what we had with the perceptron learning algorithm. We complained a little bit that it's too deep in the blue region, and when you look at the other guy, which is the pocket algorithm, it looks better. It actually does what we thought it would do. It separates them better, okay? Still, obviously, you know, it cannot separate them perfectly. Nothing can, because they're not linearly separable, okay? On the other hand, this is a good hypothesis to report, okay? So with this very simple algorithm, you can actually deal with general inseparable data, but inseparable data in the sense that it's basically separable. However, it really has some, you know, this guy is bad and this guy is bad. There is nothing we can do about them, but there are few, so we will just settle for this. We will see that there are other cases of inseparable data that is truly inseparable, in which we have to do something a little bit more drastic. Okay?